We've got a system or coupled pair of differential equations here. The concentration of antibiotic in the blood of the patient and how that's changing with respect to time versus the rate of change of the concentration of the antibiotic in tissue. We're asked to show that we can change it into a second order differential equation just in terms of y and t. All right, well, the first thing I'm going to do is differentiate the right-hand equation, because then we'll get the second derivative. And this will equal 0.032 times the first derivative of x with respect to t minus 0.025 times dy by dt. So this bit is sorted, this bit is sorted, but I want to get dx by dt now in terms of y. So I can straight away just go 0.032 and sub in this 0.025y minus 0.045x plus 2 minus that 0.025 dy by dt. Okay, so let's just multiply this out. This ends up giving 1 over 1, I wrote it as a fraction, 1 over 1,250y minus 9 over 6,250x. The other one's not too bad, it's plus 0.064. And then again, we've got our minus 0.025 dy by dt. Okay, I've just got one more little thing to do because I can now use this one again and make x the subject. So x is going to equal dy by dt plus 0.025y divided by 0.032. So I'm going to replace this by this. I therefore get 1 over 1,250y minus 9 over 6,250 multiplied by dy by dt plus 0.025y over 0.032. That's me subbing in for it. And don't forget we've got plus 0.064 and minus 0.025 dy by dt. Okay, we just got to keep going. We're not far away, so just expand that bracket. Get minus 9 over 200. Use your calculator for all of this, of course. Dy by dt minus 9 over 8,000 y plus 0.065 minus that. So, what is that? Okay, now just bring things together. We get, let's just write this out again. Second derivative becomes minus 13 over 40,000 y minus 7 over 100 dy by dt plus 0.064. And then I'm going to times through by 40,000. Minus 13y minus 2,800 dy by dt was 2,560. And finally, remember, we're being asked to write it as this, so just rearrange. Okay, and there we have it, our second order differential equation y and the t. So of course, now we're being asked to solve it. Find a general solution for the concentration of the antibiotic at the patient's tissue at time t minutes after treatment began. That is precisely y. So the first thing we're going to do is make this equal to 0 and look at the complementary function. What value of y makes that 0? And then we'll find the value of y that also gives the 2560. And the method is to let y equal a constant times e to the mt. You differentiate to then give dy by dt equal to my, and the second derivative is then going to be m squared y. We can then sub that in and basically divide through by y, and it leaves us with 40,000 m squared. We get this, what we call the auxiliary equation, plus 2,800 m plus 13 equal to 0, a quadratic to solve to find m, which we can then put into here. And we can use our calculator for this. It ends up being m is equal to minus 1 over 200 or minus 13 over 200, which means YCF is going to be a e to the minus 1 over 200t plus a different constant times e to the minus 13 over 200t. Now for our particular integral, we're going to try and find a y that is going to mean once we differentiate it, etc., we're going to get 2560. This comes with practice, but like we couldn't ever let y be a function of t, for example, because there's no way a function of t here could equal 2560. Y, in fact, is going to have to be a constant. So we're going to try y equals simply to k. Then the second and first derivatives are going to disappear, and we're just going to get 13k equals 2560. Of course, if the right-hand side was something more complicated, I don't know, e to the x or sine x or some polynomial in x, yeah, we'd have to do a different trial. So that I'm not going to go into more detail on that here. This is just a constant, so stick with that. So k is going to be 2560 over 13. And that means that that was pi. So the general solution is then these two added together. So it's going to be a e to the minus 1 over 200 t plus b e to the minus 13 over 200 t plus 2560 over 13. Okay, nice one. Now, we're asked to find a particular solution for the concentration of the antibiotic at time t minutes. Okay, let's just look through for any initial conditions. Well, we're told initially there's none of the antibiotic in the patient. So t equals 0 means that x equals 0 and y equals 0. But if we then substitute that into here, we'll see that also when t is 0, because x is 0 and y is 0, dy by dt must equal 0. All right, and we can now use these conditions in our equation. Dx by dt initially would have been 2. So let's sub in. We're going to get 0 equals a plus b, because remember e to the 0 is just 1, plus 2560 over 13. So that means a plus b is going to be minus 2560 over 13. I'll deal with that in a minute. And I've also got this dy by dt, so let's find the derivative of the general solution and then set it equal to 0. So I'm going to get minus 1 over 200a e to the minus 1 over 200t minus 13 over 200b e to the minus 13 over 200t, and that's it. So then 0 is going to equal minus 1 over 200a minus 13 over 200b when I put t equals 0 in. And I can times through by 200. I'm going to get that a is equal to minus 13b. Now let's sub this in for here. So that means 0 is going to equal minus 12b plus 2560 over 13. And b ends up equaling 640 over 39. Then we can also work out a from that. It ends up being minus 640 over 3. So y particular solution is equal to 2560 over 13 minus 640 over 3 e to the minus 1 over 200t plus 640 over 39 e to the minus 13 over 200t. Okay, well done so far. Finally, to be effective for the patient, the concentration of antibiotic in the tissue must eventually reach a level between 185 and 200 milligrams per milliliter. That's the unit we've been measuring in throughout. Determine whether the rate of administration of the antibiotic is effective for the patient, giving a reason for your answer. So what we can take a look at is what happens as t approaches infinity, because then these are going to tend to 0. As t tends to infinity. I mean, I don't know what the maximum is, but it does say it must eventually reach a level. You can see like the model has its flaws because it's kind of saying that the antibiotic is going to like then stay there forever. But in any case, like it's not, it's a fairly complicated problem that we're modeling here. So as t approaches infinity, e to the minus kt is going to approach 0 for k greater than 0. So the particular solution is going to approach 2560 over 13, which is 196.923. And this is in between 185 and 200. So the administration is effective. Well done.